Thank you, Katja. Yeah, good morning and hello also from my side. I'm glad that I can present you today one of our developed calculation tools, the so-called Autarky tool. So before I go into the details of the tool itself, I would just like to give you a quick overview on all three of our tools. So in addition to the Autarky tool, which is a web application and made for the general public, so that there's just a little previous knowledge necessary to use these tools, we have also developed two more tools which are dedicated to, let's say, the bit more advanced users. The first one is the optimal sizing calculator. This is an Excel-based tool with a Python interface, which is available download on our homepage. And this tool allows you to optimize the size of a PV system in combination with an electrical storage. And our last tool, the third one, is the optimal heat source scheduler. This tool enables you to calculate optimal control strategy of several heat producers for the next 24 hours in combination with a thermal storage. But you will hear more about these tools later on from my colleague Philip Lucavina. So let's now talk about the Autarky tool. So what are our goals and motivation for the tool? We wanted to develop a tool with the Autarky tool, which shows the potentials of electrical storages and provides the user with a technical, economic, and ecological evaluation of different producer and storage constellations. As already mentioned, the tool is made for a general public, like, for example, for household owners who wants to install a PV system on the roof, and they're not sure if it makes sense to also integrate an electrical storage in combination with the PV system. So therefore, it was important for us that the tool is easy usable and that there is a high availability of the tool. Therefore, we decided to develop this tool as a web application. On this slide, you see how the tool looks like. This is the main interface of the tool. And you also see the inputs which are needed to run the calculation. So as you can see, there are only a few inputs, some about the generation units. So we need to know which type of producer is chosen, like a PV system, for example. We need to know the size of the system, the peak power. And if we would choose a photovoltaic system, we would also need to know the orientation and the inclination angle of the PV system. Then we need to define the consumer. Here we need to know which type of consumer we have, the country where it's located, and the consumption per period. And then we also need to define the storage. Here we just need to know the size of the storage in kilowatt hours and the maximum charging capacity of the converter. And then we can also change the evaluation period. So by default, 1 year is used for the calculation, but it's also possible to have a detailed look on, for example, a summer or a winter month. And if you have inserted all these inputs, you can click on the calculate button, and after a few seconds, you will get the results for the chosen scenario. But before I show you some example calculations in the tool itself, I would just like to give you a few more background information about the input data and the calculation method we have used for the tool. So if we have a look at the producer, here you can choose between a photovoltaic system, a wind energy turbine, and a small-scale hydropower plant. So I would say the main focus of the tool is on the photovoltaic system. Therefore, I will also mainly or sometimes say just photovoltaic system when I mean producers, but it's also possible to choose a wind energy and small-scale hydropower. For PV systems, it's necessary to as input to include the peak power, the orientation, and the inclination. And based on this input and on an global radiation profile, which is already included in the tool, the production profile will be calculated for 1 year. The same is with wind energy and small-scale hydropower. Here we use measured data from an Austrian plant, which are scaled with the peak power, which is in user input. Then the second thing is that we need to define the consumer. Here you can choose between several different household profiles, but we've also included industrial profiles and also some other profiles like a car floor and slope elevator. So if you're wondering now why we have included these two profiles, as most likely no one of you will own a car floor and slope elevator, this is because these two are based on two of our pilot plants, the Project Castle in Croatia and the slope elevator in Cuneo, Italy, which you will also hear more about it later on. If we have a bit detailed look on the household profiles, here you can choose between single households, double households, and family households. And we also make the differentiation between people who mainly stay at home, for example, if they are retired, or people who normally goes to work during work days, as this also has an influence on the autarky rate. So as you can imagine, if someone goes to work, the most electricity will need it in the morning and evening hours. So which is normally not the time the most PV production is available. So if we choose such a profile, the autarky rate will most likely will be lower than if we choose a profile where the most energy is needing during midday. And yeah, all of these profiles are generated generically with the so-called load profile generator. This is a free online tool, which in my opinion is a quite good option to generate such profiles, which are very close to real measured profiles. For the industrial profile, we've used several different standard load profiles. And as already said, the castle, slope, elevator, and so on are based on the measurement data of the pilot plant. And after you've chosen one of these profiles, the profile will be scaled with the annual energy demand, which is also a user input. Yeah, and then the last thing we need to define is the storage. Here we only need to define the size of the storage and the maximum charging capacity. Everything else, like the storage losses, are calculated internally. Here we have implemented a model which calculates the losses based on the relation between the maximum and the actual charging and power of each calculation time step. Yeah, how is the storage charged and discharged? Here we follow three priorities. The first priority is always to use the PV production directly, so without the storage, and only if the PV production is higher than the demand at this moment, then the storage will be charged. And only if these two priorities are not possible, the electricity surplus will be fed in the public grid, like for example, if the storage is already full. And the same accounts the other way around for the discharging and purchasing the electricity from the public grid. Yes, that's basically all the inputs we will need to enter in the tool. And if you click on the calculate button, then you come to this result page you see on this slide here, where you get, as already mentioned, the economic evaluation, the ecological evaluation, and the technical evaluation. If you have a look at the economic output, here the first value is a reference value for the energy costs for 100% grid consumption, so without storage and without a PV system, for example. The second one are the energy costs with storage and with a producer, so are the energy costs for the chosen scenario. Then we see the energy savings, which is the difference between these two values, and we also get an estimation for the amortization period. As you have seen, there are no inputs for electricity prices, feed-in tariffs, or investment costs necessary. This is because we use some mean values per country. So depending on which country you choose, there are already some mean values included in the tool, which are used for this calculation. This is because we want to want to make the tool as simple as possible. But this also means, of course, that especially for the amortization period, we need to say that this is an estimation, as especially investment costs can vary quite a lot depending on which storage type is choosing or how the roof looks like and which founding possibilities can actually be applied. But still, it gives the user a good idea if a chosen configuration would make sense from the economic from an economic point of view. Then we have the ecological evaluation in the form of a CO2 emission savings, which can be reached due to the integration of the producer and the storage. And we also get some technical outputs, especially the autarky rate, of course. So in this slide, you see a few more details about the technical evaluation. First, the autarky rate, which is an indicator of the independency of our system, calculated with the self-used share of the own production with the PV system divided through to the total energy demand, and also the own consumption rate, which is an indicator of how much energy of our own production can actually be used. So if we would have a high own consumption rate, for example, and a low autarky rate, this would mean that we have a rather small PV system installed on our roof. so that we can almost use all of the production on our own, but that we still need to purchase a higher share of energy from the public grid. Then you will see the storage efficiency and the storage losses. So here you see if the storage size and the maximum charging capacity is chosen appropriately. We get the time of self-supply, and it's also possible to create a so-called checklist. This is a PDF document which serves three main purposes. The first one, on the first pages, there is a summary of the input data and of the results. So it's a good and easy possibility to save our calculation results. On the next pages, the user gets an additional explanation of the calculation results based on the actual results. So for example, if we would have an Autarky rate of 41%, then there will be an evaluation what an Autarky rate in this range would mean for our systems. And in the last part of the checklist, there are also some advices for those who want to implement the storage in historical urban centers. So the tool can be used generally, not only in historical urban centers, but we also provide some specific advices here, as this is one of the main focuses of the Store4HUC project. Yeah, let's now have a look on the tool itself.
Robert, sorry, you have 1 or 2 minutes.
Yeah, okay, I will hurry.
Just for the reminder.
You can reach the tool with this direct link or with the Store4HUC homepage. So then just let me show you one quick calculation. We could choose one PV system with 5 kilowatt, for example, for a mean or for an average family household. Let's say it's located in Germany, and we can say first that we do not have a storage, for example. And then click on the calculate button, and after a few seconds, you will get the results. And you will see that with this configuration, for example, we could reach an Autarky rate of 31%, an own consumption rate of 42%. You will see that we have energy cost saving of almost 900 euros, and then we would need 11 years to pay off the investment costs. Now we could include one smaller storage, for example, and see which influence the storage would have on our results. And yeah, as expected, the Autarky rate is increased. Also the own consumption rate, you see that the energy cost savings are also a bit higher with more than 1,000 euros. And the amortization period is also slightly higher with 12 years. This is because of the additional investment costs we have for the storage. Here you can create the checklist. And if you need some additional information, you can move your cursor to these info boxes. Here you get some information about the necessary inputs. Or you can click here on the show tool information button, where you get a short additional explanation of the tool. And there is also a link to a YouTube tutorial where the tool is explained, and a link to the background information document. And here you can also change the language of the tool. Yeah, now you could start to play a bit around with the numbers and see what, for example, a larger storage would have, which influence it would have on your system. Yeah. Let's stop here. I hope I could motivate you to have a look on the tool on your own, and I would be glad to answer all your questions. Thank you.
Thank you, Robert, for this enlightening presentation. Now Robert will answer some questions if there are some. So audience, it's your turn. Wolfgang, you raised the hand. Please unmute yourself.
Sorry. At the moment, the energy prices are going up quite fast in Germany. And I ask myself, what do you think? Does it make storage more interesting if electricity costs are increasing? And I saw that you calculated with a certain, I don't know, price for electricity in the back end. So if it changes every few months, or if it's going up, you should change the numbers in the back end as well. No?
Yes, that's right, of course. So we do constant updates of the tool. When you look at the at bottom of the tool, you will see that we have done the last update in mid-January. So the numbers will be updated also after the project ends to ensure that it's also the results are up to date. And to answer your second questions, yes, I think so, but it of course also depends if the feed-in tariffs goes up. So if the electricity prices goes up and the feed-in tariffs goes up, then you also get more money if you feed in the electricity surplus directly in the public grid. So it's always dependent on which tariffs you have here. So for a certain time in Austria, we had, for example, the special situation that the feed-in tariffs have been sometimes higher than the tariffs for the consumption or for the purchase from the grid. So in this case, it would have made sense just to feed in all your PV production in the grid, but this was just a situation for a few months, and I'm expecting that this will change again. And then I think that storages might be very interesting also if you want to be independent from the grid and have a high autarky rate.